Welcome back to the AutoML lecture series. My name is Jovita Lukasic and we will talk about neural architecture search. In this first part, I will explain what neural architecture search is. So, what we all normally do in deep learning in order to actually find a high-performing neural network on a downstream task of interest, here for example on ImageNet for image classification, is to define a network topology. So, how deep is my network? How wide is my network? What kind of layers and how do I want to connect these layers with each other from various configuration options available? And of course, I need to decide what kind of layer types do I want to actually use, ranging from a vast amount of convolution layers to pooling to nonlinearities. With the overall goal in classical deep learning to find a high scoring and efficient network, we also face some limitations when we do it actually all manually. It's a very time-consuming process and it involves a lot of trial and error. So as soon as I change either the depth of my network or some kind of operation on a certain layer, I need to assess, did this change actually improve or decrease the performance of my neural network? It's also based on a lot of expert knowledge. Here, for the example, Google network from 2015 looks very complex and is a result of years of trial and error by experts and actually to achieve such a complex state-of-the-art architecture. Neural architecture search, in short NAS, is an option to overcome this manual design. So neural architecture search aims to find a neural network with a strong performance in an automatic and efficient way on a downstream task of interest. Therefore, we want to overcome the limitations of the manual design of neural networks. It's also an intensely researched research field, which we can also see here in this figure, where the amount of paper increases over the actual years and times this research field came out. However, initial methods are extremely expensive and becoming more and more efficient in terms of needing less compute resources, as well as needing less evaluated neural networks. NAS is not only very well performing and improving over human-designed networks for ImageNet, image classification, but also for a wide range of a diverse data set, ranging of course from computer vision to audio classification, PDE solvers, protein folding, as well as medical diagnostics, showing the ability of NAS-found networks in comparison to human-designed ones. Additionally, where neural architecture search is very important is robustness awareness, especially in the area of computer vision. Here we can see an example of a panda, where the Google net, which we have seen several slides ago, also predicts a panda and has a confidence of 58%. As soon as we add very little noise to it, the prediction changes to a gibbon, but the confidence of the Google net increases. So it predicts a gibbon and is to 99.3% sure that the image it sees is a gibbon. However, our human perception did not change just with this little noise. This leads to the issue that already slight perturbations on the input data can easily cause misclassification on deep learning networks. In the context of NAS, the goal is to find an architecture with a good clean accuracy as well as robust accuracy and its trade-off. What we want is, here for example on the right figure, to come to the upper right corner, so having a high standard accuracy and a high robust accuracy. The challenge we face in robustness-aware neural architecture search is that evaluating the robust accuracy requires a fully trained network, which is additionally very expensive. A different area where NAS is showing impressive results is hardware awareness. So architectures must run efficiently on specific hardware targets depending on your actual downstream task of interest. Not everything is running on a GPU, ranging from mobile CPUs to embedded FPGAs. In addition, the same architecture can have very different latencies depending on the actual hardware it is deployed on. So therefore, hardware-aware NAS aims to search for an efficient and high-performing architectures in an automatic way. Important to note here is that only a single global efficiency matrix, for example the number of flops, which is normally used in order to design an efficient network by hand, is insufficient, since hardware-specific profiling is needed, as already mentioned, different latencies depending on the actual hardware. So what we want is to find a deep learning model which can be deployed on different hardware types ranging from an FPGA to a microcontroller. This is often used in a multi-objective setting. So how can we incorporate hardware costs, for example, into NAS? There exist two main approaches. The first one is a constraint search, where we add a latency or memory constraint given the data set, the downstream task of interest, as well as the hardware we want to use, and search for the best accuracy actually satisfying this constraint. It's a direct approach, allows to easily include these hard constraints, and they are easy to communicate. However, this approach requires a rerunning of the search for each different constraint value tau. So if the latency or memory constraint changes, we also need to do the rerunning of the search. A different approach is the multi-objective search, here on the example of scalarization, which combines two objectives into a single weighted sum or more objectives as well. So we have an architecture A, and we have the costs of our architectures. Here, for example, the costs of the accuracy of the architectures, which can be, for example, the loss or the performance. And we have a weighted sum, so we have the cost of the architecture plus a hyperparameter lambda or parameter lambda times the cost of the hardware of this architecture A. For example, a latency or memory costs. And the lambda controls the trade-off. So how much do I actually want to weigh both things together? If I want to have a complete joint optimization where both things are important to me, the accuracy, high accuracy, as well as, for example, a low latency, I have to set lambda to 1, for example. And changing lambda moves along the Pareto front of this multi-objective search. We can see here also on this figure that neural architecture search, are the yellow circles, also improved over actually handcrafted neural networks. So the bigger the circle, the more inefficient the network is in terms of the number of parameters, and the more to the top the architecture is, the higher is the accuracy. What we can see is, for example, that hardware awareness, which are the green circles, in this context of efficient net, actually achieves very high accuracy, top 1 accuracy, but with a lot less number of parameters, improving over actual current searched, handcrafted search, which are the red buttons, the red circles. So everything NAS related actually improves over efficiently handcrafted networks. Of course, the larger the network, the bigger the network, the more parameters the network has, the accuracy can increase. Coming back to the neural architecture search definition itself. Neural architecture search is based on 3 different components. We have the search space, we have the search strategy, which we apply within the search space, and we have a performance estimation strategy, which actually estimates how good is my performance of the architecture and giving this information back to the search strategy in a loop. So, to summarize what we have just talked about in the last minutes, NAS aims to automate the time-consuming process of designing neural networks by hand. It has shown the ability to perform very well and high on a diverse set of different data sets, and also improve over human-designed neural networks. Particularly important is that NAS is able to achieve high performance using multiple objectives simultaneously. For example, robustness awareness, or dealing with different hardware constraints in both constraint as well as multi-objective search scenarios. So I hope I gave you a very good overview about what neural architecture search is, and hope to see you in the next video.